In episode 49, Recap Checkpoint, Implementation and Testing Essentials, we pause to consolidate lessons from the build and test journey you have followed across the last several episodes. Up to this point, we have moved from writing secure code to integrating controls, planning layered testing, and turning results into meaningful risk reduction. A checkpoint like this is not just a summary. It is an opportunity to simplify the story into a set of habits you can recall under exam pressure and in real projects. By revisiting the key ideas in one place, you can see how design, implementation, and testing practices reinforce each other. That holistic view is exactly what an exam is expected to bring to complex environments. A natural place to start is with the secure coding habits that quietly shape everything else. You have seen how disciplined input handling, explicit validation, and clear normalization reduce the attack surface long before tests run. Error management patterns matter just as much because verbose stack traces, inconsistent codes, and mixed user messages can turn minor mistakes into useful attacker tools. Throughout, the emphasis has been on avoiding anti-patterns such as trusting client-side checks, mixing control and data without encoding, or logging secrets in plain text. When developers adopt these habits early, testing becomes a confirmation of good practice instead of a scramble to find and patch avoidable weaknesses. From there, it helps to remember how control implementation priorities were framed. We focused on choosing secure defaults, establishing correct initialization order, and designing failure behaviors that degrade safely rather than catastrophically. That means, for example, enabling strict transport settings by default, enforcing authentication before exposing sensitive functionality, and treating missing configuration as a reason to fail closed. Initialization ordering ensures that key controls, such as logging, encryption, and access control hooks, are active before services accept real traffic. When failure does occur, the system should prefer to stop or limit functionality rather than quietly continue in an unknown state. Integration guardrails have been another recurring thread because most real issues appear where systems meet. You saw how well-defined contracts between services, strong input validation at boundaries, and impotent operations keep distributed systems predictable under stress. Back pressure mechanisms under load, such as queue limits and throttling, help prevent one misbehaving component from cascading failures into the rest of the environment. These guardrails are not purely performance concerns, they are security concerns as well, because they determine how the system behaves when stressed by both legitimate surges and malicious traffic. When integration points are treated as first-class control locations, you avoid the illusion that security can be bolted on after the fact. Pipeline hardening pulled those ideas into the delivery machinery itself. We highlighted the importance of signing artifacts, tracking provenance through the build chain, and isolating pipeline components so that compromise of one step does not poison the whole release. Staged verification gates, which may include static analysis, dependency checks, and targeted dynamic tests, create repeated opportunities to catch issues before they reach production. By treating the software development lifecycle, SDLC, as a security-relevant system in its own right, you gain trust not just in the code you ship, but in how it was produced. That trust becomes critical evidence during assessments and when explaining your posture to customers and auditors. Testing strategy came into focus as a layered, risk-based construct rather than a single event. You saw how unit, integration, system, and acceptance testing each have distinct roles, and how security checks can be placed at each level with intent. Risk-based prioritization ensures that high-impact paths, sensitive data flows, and externally exposed services receive proportionally more attention than low-impact internal utilities. The strategy stretches across environments and releases, from early design reviews and static analysis to pre-release penetration tests and post-deployment monitoring. When you view this landscape as one integrated plan, you see how each layer catches different classes of issues and supports different kinds of assurance. Attack surface test case design was introduced as a way to make testing deliberate rather than exploratory guesswork. The emphasis was on deriving hypotheses from threats, incidents, and architecture, then turning them into specific cases with clear preconditions, triggers, payloads, and expected outcomes. You also saw the value of covering unauthenticated, authenticated, and privilege escalation paths, and of including abuse cases that treat features as potential attack tools. High-yield patterns came from strong observability and well-defined oracles, so testers could tell quickly whether a scenario revealed a problem. This discipline turns a long list of endpoints into a curated set of experiments that consistently surface meaningful findings. Automation through interactive application security testing, IAST, and dynamic application security testing rounded out the continuous coverage story. We discussed tuning tools to understand your stack, authentication flows and protocols, and configuring them with realistic constraints so they behave like informed testers rather than blunt instruments. Scheduling scans per build, nightly, and pre-release created a pattern where regressions are caught early and often, while safe profiles, rate limits, and maintenance windows protected production environments. When IAST insights are correlated with DAST observations, the organization can move rapidly from symptom to precise root cause. The result is a quieter, more reliable signal that teams are willing to act on. Penetration and fuzz testing sat at the deep end of the testing pool, where intensity is high and objectives must be clear. You saw how purposeful engagements begin with defined goals, rules of engagement, and safety constraints, and how blending black box, gray box, and white box perspectives yields richer findings. Vulnerability chaining illustrated how small issues combine into serious impact, while fuzzing strategies explored resilience beyond expected use. Retest practices and coordinated fix cycles ensured that these demanding efforts produce lasting improvements rather than one-time drama. This view repositions penetration and fuzz testing as targeted instruments in a broader program, not isolated heroics. Documentation verification and drift detection reminded you that systems do not always behave as described. We walked through comparing policies, standards, and procedures with implemented controls, checking live data flows and interfaces against diagrams and specifications, and using telemetry to reconcile expectations with reality. You also saw the importance of uncovering undocumented behaviors, such as shadow endpoints, legacy paths, and quiet configuration switches that still influence security posture. Recurring drift detection mechanisms turned this from a one-off exercise into a continuous practice. Together, these techniques ensure that written assurances remain anchored to the actual environment. Defect management themes tied analysis back to improvement. We revisited the importance of consolidating findings from multiple tools and tests, normalizing severity, and deduplicating issues to reveal underlying root causes. Capturing clear reproduction steps, ownership, due dates, and dependencies made it possible to move from discovery to resolution without losing context. Trend metrics, such as mean time to remediate and escape rates, turned defect tracking into an indicator of systemic health rather than a static list. Rigor in retesting ensured that resolved issues stayed resolved and that regression suites captured lessons learned. Along the way, you have seen common pitfalls and the simple habits that prevent them from recurring. Examples include over-relying on unauthenticated testing while ignoring deeper roles, treating non-production data as harmless, or assuming that past scan equals controlled risk. The counter habits are straightforward. Maintain explicit scope and risk maps, design tests from hypotheses, treat test data as a regulated asset, and link every significant finding back to a requirement or threat. These small, repeatable behaviors are what separate ad hoc security efforts from mature, exam-ready practice. They are also what make complex systems more predictable over time. A quick mental review of this checkpoint shows a coherent set of essentials rather than a scattered list. Implementation discipline, from coding to configuration, sets the stage for meaningful testing. Testing strategy, from surface analysis to deep penetration and fuzzing, reveals how those implementations behave under pressure. Verification of documentation, careful defect triage, and trend-based improvement cycles ensure that what you learn is turned into durable change. As gaps become visible, they immediately suggest where to invest next, either in stronger patterns, better tooling, or clearer governance. That forward view is itself a key part of professional assurance. The practical conclusion for episode 49 is to translate this recap into focused reinforcement. Choosing two areas, such as attack surface test case design and defect triage discipline, and planning a short, structured rehearsal around each can deepen your skills quickly. In one session, you might design a handful of high-quality test cases for a known interface. In another, you might take real or sample findings and drive them through normalization, linking, and prioritization. By rehearsing in this way, you turn conceptual understanding into muscle memory. For an exam candidate, that is the bridge between reading about assurance and delivering it. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.